In this paper, we present ARGUS, a visualization system to debug and understand AI-assisted task guidance in augmented reality. The concept of an augmented reality, or AR assistant, has captured the human imagination for years, as the applications of such a system are seemingly endless. Humans, even those with domain expertise, have imperfect memories and skills which deteriorate over time, especially during repetitive tasks or under stress. The aid of an AR assistant can reduce human error via corrective feedback, improve performance by reducing cognitive load, and introduce new tasks across a wide variety of applications. Common use cases for such systems include supporting performers in repair and maintenance tasks, in manufacturing, specifically training or live monitoring of production lines, and in healthcare and medicine, to assist in surgery or other procedures. Moreover, digital assistants can also make use of AR to enable a virtual embodiment of the assistant. Between the recent explosion of machine learning research, particularly the creation of powerful models able to detect objects, actions, and speech in real time with high accuracy, and the commercial availability of AR headsets, we now have the technology to begin developing the type of assistant once relegated to science fiction. Yet the development of intelligent AR assistants is complex and computationally expensive. An effective assistant must be able to perceive the environment, model the performer's actions, and reason through the consequences of a given action on the state of the environment in order to provide useful feedback. It also requires a user interface with which to interact with the performer. Meeting these requirements involves orchestrating multiple and heterogeneous services, particularly processing real-time sensor data for action and object recognition, as well as reasoning. This, in turn, requires collecting, storing, and accessing a large volume of annotated data for model training. Additionally, this system must model performer behavior based on first-person perspective data collected by the AR headset. To debug such a complex system, developers must be able to analyze multi-resolution data both during and after a task session. The idea of using AR technologies to build assistive systems with an internal model of the real world and the ability to augment what a performer sees with virtual content dates back more than 3 decades. However, only recent advances in AR display technologies and AI, combined with the processing power to run relevant computations in real time, have enabled us to start building such systems. The development of visualization systems to debug and understand the data acquired by multimodal integrative AI applications has quickly followed. These include Microsoft's Platform for Situated Intelligence Studio and Foxglove Studio, a debugging tool for robotics data. Each requires users to tailor the structure of their data to the system. Both focus on visualizing individual data streams and are not able to summarize long periods of recordings with visualizations. To the best of our knowledge, existing tools also lack the ability to debug relevant ML models. Other visualization tools, such as Manifold, are tailored to the interpretation and debugging of general ML models. We are specifically interested in ML models that pertain to the behavior of AR assistants, which have different requirements than other visualization systems. Let's explore a simple task guidance scenario that highlights the gap we aim to bridge with our visual analytics system, ARGUS. Consider a recipe, which requires a performer to use multiple utensils to combine several ingredients and produce a final meal. In order for the AR assistant to guide the performer through the steps of the recipe, multiple components must work simultaneously. These modules use the multimodal data produced by an AR headset to try to understand the performer's environment as well as their actions, and in turn infer the current step of the recipe and identify possible performer errors. All modules communicate via a streaming database that allows for the easy collection of any data produced during a session. ARGUS then provides users with comprehensive visualizations of how these different modules are behaving, enabling them to understand and fix system failures or propose improvements. For instance, while trying to understand why a model has stopped detecting a specific object, we may look at the detection likelihood for each object in the recipe at a given frame. This same strategy can be applied to the whole video in order to capture possible detection patterns of the model. In doing so, we quickly recognize that the model stopped detecting the cutting board for a long period of the recording. We propose several potential explanations for this behavior. Perhaps the performer was looking in a different direction, or the appearance of the cutting board changed due to being obscured by another object or a change in lighting conditions, confusing the model. Perhaps the system was overloaded and the perception modules stopped working. ARGUS enables us to investigate these hypotheses and determine the cause of the error by presenting highly detailed information about every component of the AR assistance system. ARGUS was built within the context of the Perceptually Enabled Task Guidance Program, an initiative of the Defense Advanced Research Projects Agency, or DARPA, which seeks to develop the first generation of robust AI assistants. Over a multi-year effort, our team collected feedback from domain experts in various fields, incorporating input both from experts actively working on the project and other AR developers aiming to build interfaces to support task guidance. In accordance with the needs of these experts, ARGUS provides live monitoring tools for real-time analysis during task sessions, enables transparent acquisition and indexing of data from task recordings, and implements a set of interactive tools that facilitate retrospective analysis of collected data. Please refer to our paper for more details on the system background, features, and design process. The online mode of ARGUS uses data collected by an AR headset to interpret the state of the environment and performer behavior as they execute a task. The online mode also highlights potential model errors, allowing a user to adjust model thresholds in real time. It includes the streaming video player, which allows users to inspect the output of an AR headset's main camera, overlaid with bounding boxes representing detected objects. The online mode display also lists these detected objects that are identified by perception models, as well as their corresponding number of instances. A subset of these are highlighted as target objects, which are needed for the current step of the task. The confidence controller allows the user to control the threshold for model confidence. The online mode also includes reasoning model outputs, including the step and error predictions, predicted step description, and the performer's status. Additional widgets show the predicted actions with their probabilities. Finally, the online mode displays the raw data collected by the system. Users have the option to record all data captured and generated by the AR headset sensors and associated ML models during a session. Over time, the online mode of ARGUS enables researchers to collect recordings from different users, creating a database of historical data containing valuable knowledge to be explored by researchers via the ARGUS offline mode. Users can begin interacting with ARGUS's offline mode by filtering for recordings of interest. The Data Manager panel allows users to define parameters, such as the recording duration, and search for recordings that fulfill the defined criteria. ARGUS's spatial view provides an intuitive understanding of how the performer interacted with their environment during a task. The basis of this component is a representation of the environment where the task took place in the form of a point cloud. We use the HoloLens 2 AR headset, which generates a point cloud representation of the environment every half second based on the RGB and depth frames it captures. Once a performer ends a task, a pre-processing step takes place. ARGUS merges all the point clouds produced during the recording of a task into one large point cloud. However, to allow for the transference and rendering of this point cloud from the file server to the client within a reasonable time frame, a voxelization-based sampling process takes place to reduce the size of the point cloud before it gets persisted to our file server, allowing users to load them into ARGUS's interface in less than 2 seconds. This voxelization process produces a final point cloud representing the environment at a 1 centimeter resolution, providing a detailed scene for users to analyze. With this representation in place, the user can overlay different data streams onto the scene, summarizing the performer's actions. For example, one can render a heat map summarizing the performer's position during the task, allowing the user of ARGUS to understand regions where the performer spent most of their time. The same can be done using gaze information captured by the eye trackers built into the HoloLens headset. The orange heat map shows regions the performer spent time looking at. This heat map also allows the user to quickly identify regions the performer spent time interacting with. This same information is available for hand position and detected objects. Finally, users can obtain more detailed information from this component by hovering their mouse over specific points representing where the performer was at a particular time, which highlights the performer's gaze direction. This interaction also updates the temporal view, which we will explore next. ARGUS provides a model debugger based on temporal visualizations tailored to the ML models used in AI assistant systems. It has 2 main components. 1, the video player with a panorama stitching mode, and 2, the model output viewer. The video player, where we display the raw main camera video stream collected by a HoloLens 2 headset, enables a highly granular level of model debugging. This allows the user to note specific frames where object detection failed or yielded unexpected results. However, the main camera of many AR headsets has a limited field of view. Often objects that the performer sees at a given time step are not within the view of the main camera video at that time step. We thus aggregate frames into a series of panoramic mosaics in the second view of the video player component, capturing a broader scope of what the performer can see. We generate these panoramic mosaics by sampling frames from a temporal window centered around the current time step. We observe that these panoramic mosaics expand the view of the scene significantly, revealing objects within the view of the performer at a given time step that were not captured by the main camera at that same time step. The model output viewer provides a visual summary of the temporal distribution of the model outputs. It has three main components: the model outputs, the confidence matrix, and the global summaries. Model outputs are grouped by objects, actions, and steps. In the confidence matrix, each cell is colored according to the confidence score of the detected item at time t, from 0% to 100%. The global summaries show the average confidence and detection coverage for each row. Taken together, these allow users to quickly and easily evaluate each object, action, or step in a scene. Now we will show a case study where a user of ARGUS wants to summarize the performer behavior during a session and look for potential model failures. First, the user loads a session and inspects the point cloud to understand the environment where the session took place. After that, making use of the 3D heat maps available in ARGUS, the user quickly spots 3 darker regions where the performer spent most of their time interacting with the scene. Then, using the 3D points, the user highlights specific frames and realizes that the rightmost of these 3 dark regions represents the portion of the session where the performer was interacting with the online mode of ARGUS to start a recording. The user also sees that the center region is where most of the performer's actions took place, and finally that the leftmost region is where the tortillas were stored. The user can now use ARGUS to understand model behavior during the session. First, by looking at the occupancy map, the user certifies that more objects were detected in the center region in comparison to the left region, both of which are located on the desk where the performer was working. Lastly, the user can inspect the spatial distribution of specific objects. They begin by looking for where tortillas were during the session. 2 clusters appear, one representing a bag of tortillas and the other a single tortilla. The user sees this same pattern arise with the cutting board. However, while inspecting the frames, the user sees that the leftmost cluster contains mostly false positives for the cutting board class. In the future, we intend to conduct a deeper evaluation of our system's performance metrics, as well as explore how to extend the system to support the comparison of sessions with multiple performers. Since our temporal and spatial views allow users to explore data across the entire session, adding annotation capabilities is another natural next step. Finally, we wish to investigate privacy-preserving methods for storing and streaming the collected data so as to prevent performer identification. This work was supported by the DARPA PTG program. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of DARPA. Thank you for watching.